All right, we're going to work this question where we need to find the local and absolute extreme values of the function f of x equal to x cubed times e to the negative 3x on the interval from -1 to 3. We need to find critical values, so that means we need to find the first derivative of this function, which is going to involve the product rule because we've got these two things being multiplied together. So in order to find the first derivative, we need the derivative of x cubed, which is 3x squared, and then times e to the negative 3x, plus, to complete the product rule, we leave x cubed alone, we already took that derivative, times the derivative of e to the negative 3x, which is itself, and then chain rule times negative 3. This results in 3x squared over e to the 3x minus 3x cubed over e to the 3x. And I can do some factoring here, and this is going to be useful in finding critical points. And I can factor out a common 3x squared over e to the 3x, leaving me with 1 minus x on the inside. So now looking at this, in order to find critical points, I look at where the first derivative is undefined, and I also look at where the first derivative is 0. There is no x value for which the derivative is undefined. I'm not going to get 0 in the denominator there. I've got e to the 3x. It doesn't matter what real number I choose for x. I'm never going to have 0 in the bottom. So that leaves me with when is f prime equal to 0? And so I think about 3x squared over e to the 3x times 1 minus x equal to 0. Then I'm looking at setting each factor equal to 0. And that gives me the critical points x equal to 0 and x equal to 1. So I want to test these values on the closed interval that I'm given, and that closed interval is from -1 to 3. So from -1 to 3, and then I've got my critical points 0 and 1. I'm actually going to move this one over a little bit more. There we go. And I want to test all of these. Now, if 0 and 1, if one of those was not in the given interval, I wouldn't have to test around it, but they both are in this given interval. So I want to see what's going on with the function. When is it increasing? When is it decreasing? Because that helps me identify local and absolute extreme values. And so I want to test using my first derivative here. And my test values are just going to be values, let's pick green, that lie in between each one here. So I'm going to pick, say, -1/2, +1/2, and then 2 to test. You don't have to pick those, but you could pick others if you like. But those are ones that I'll choose to test, and I'll plug these into my first derivative. And when I do that, I'm going to 3 times -1/2 squared over e to the 3 times -1/2, and then times the quantity 1 minus -1/2. And notice here, well, -1/2 squared is going to be positive, so I'll have a positive in this numerator, positive up here. E to the -3/2, that's going to be positive. And then 1 minus -1/2, that's also going to be positive. So all of those are going to be positive. So my first derivative is positive in that interval, telling me that f prime is greater than 0, that f is increasing. Similarly, if I were to plug in a +1/2, I'm going to get positive again, because I'll have 3 times 1/2 squared, e to the 3/2. Those are both going to be positive, and 1 minus 1/2, that's also going to be positive. So again, I've got f is increasing on this interval. So far I have f is increasing from -1 to 0, and then from 0 to 1. At 0, f has a tangent line with slope 0. And then if I look at what's going on at 2, I'm going to get something a little different. Although I'm going to have 3 times 2 squared, that'll be positive, and e to the 3 times 2, or e to the 6, that's going to be positive. 1 minus 2, that is going to be negative. So my result here is negative. My first derivative is going to be negative, meaning that f is decreasing. So if you imagine at -1, you've got that your function is going up. You've got a horizontal slope at 0. It keeps going up. Maybe I'll draw these pictures actually. Probably use orange. We know that we're going up. We keep going up, and then we're going down. So increasing, increasing, and then decreasing. So let's look at some function values. Now, in particular, we need to look at the function values at -1, 1, and 3. The reason why we don't need to look at the function value at 0 is because there's not the possibility of a max or min there. The function increases to 0, has a horizontal slope, a slope of 0 at 0, and then it continues increasing. And so there's no possibility of having a max or a min there because we're increasing before it and after. However, we have the possibility of having extrema at -1 and 3, the endpoints, as well as the critical point 1. At the critical point 1, we can see that we're increasing and then decreasing. So we know that because we have increasing before it and decreasing after, that there's a local max at x equal to 1. What that maximum value is going to correspond to the function value. And whether or not it's also an absolute max is going to depend on what the function values are. So let's figure out what the function values are for each one of these. Now remember that the function was x cubed e to the -3x. So let's just write that down here so we don't lose track. And so we plug in -1, we're going to get -1 e to the +3. Or if we like, that's going to be just -e cubed. If we plug in 1 cubed is 1, and we're going to have e to the -3, or if we like, 1 over e cubed. And then if we plug in 3, we're going to have 3 cubed, which is 27, and then e to the -9, or 27 over e to the 9. Summarize what we have here. We know we have a local maximum at x equal to 1. We were increasing away from the x value of -1, so that's quite possibly a minimum, and then decreasing down to our x value of 3, and we've got our function values. We've got -1, comma, -e cubed, and we've got 1, comma, 1 over e cubed, and we've got 3, comma, 27 over e to the 9. And so -1, comma, -e cubed, that is going to be our absolute min. In fact, maybe more specific, the absolute min value is the function value and occurs at x equal to -1. And then we've got our local and absolute maximum of 1 over e cubed, because that is going to be a bigger number slightly than 27 over e to the 9. So we've got a local and absolute maximum of 1 over e cubed occurring at x equal to 1.